So, to continue our exploration of the relationship between two variables, today we're going to go into correlation. But let's go back a bit and let's see what we've looked at so far. So far we've looked at the odds ratio, for example. I know you've also looked at relative risk, but let's go back to the odds ratio. And that was a way of quantifying relationship between two dichotomous variables. So for example, we might look at exposure, yay, nay, and we might look at disease, yay, nay. And so we had the little 2x2 table, and we calculated the odds ratio, etc. Now, or here's another example, okay? You guys were asked this question when you did the survey, and you were asked, it was supposed to be when you rinse your hair in the morning, in your morning shower, do you face the shower head or do you turn around and rinse your hair from the back of the head? And here's what happened. 8,330 of you responded, and of the women, 60% said that they face away, so 40% said that they face the shower head, and the males, the opposite, almost the opposite. 42% faced away and 58% faced the shower head. I don't know why. Every time I do this, I ask this question in class, it comes out this way. It's a 60-40 split. I don't know why. Now, a number of people have said, oh, it must be because women have got long hair and men have short hair, and that's why it happens, and it's easier to do long hair this way than... So, okay, we asked you that question, and you responded. And indeed, if instead of sex, we asked the question, do you consider your hair to be long? And those of you who said no, we had that faced away was 48%, and 52% faced the shower. This makes sense because no is probably correlated with male. But anyway, let's continue this. Those of you who said yes, hair is long, 57% said away and 42% said towards. So there it is. The odds ratio now, this time, is 48%, 1.48, sorry. Whereas before, when we looked at the male-female odds ratio, it was 2.11, all right? Highly significant. Now it looks like also significant, but it's not as much as the 2.11, it's only 1.48, so maybe it's not this. So now we're confused, of course. Okay, was it the hair or was it the sex? It looks like probably it's the sex because it's got a higher odds ratio. But, okay, let's investigate this. So what we can do is, what I did here is I broke it up into two, because I was worried a little bit about the Joule effect, the Simpson's effect, okay, Simpson's paradox. So do you consider your hair to be long? And yes. So these are the 2,800 people who did. Of those, the females, 61%, 38.59. Of the males, 39.92, 60.8. The odds ratio, 2.4. So instead of 2.11, it's 2.4, you know? It's in fact just a smidgen more than it was before. And so the same sort of relationship maintains male-female amongst those who consider their hair to be long. How about those who consider their hair to be short? So the answer would be no. Here they are, odds ratio 2. We see the same thing. Females, 60% face away, 40% face. Males, 42% face away, and 57% face of the 5,521 who consider their hair to be short. So what are we seeing here? We're seeing that if you condition on hair length, it doesn't matter. You're still getting 2.4 and 2.0 as your odds ratio. Okay? So, all right. So then we say, all right, let's look at within a particular sex. All right, so let's look first at the females. And of you, there were 3,902 who responded, and we get that 60% face away amongst those who think that their hair is not long, and 39.86 face. Of those of you who think their hair is long, 61% faced away, and 38.59 faced. So it's the same thing, so it doesn't matter. It doesn't matter. We get the same 60% facing away, 40% facing. When you looked at the males, there were 4,419 of you who responded. And those who consider their hair not to be long, we get 43% faced away, 57.23 faced. And of those who consider their hair to be long, 39.92 faced away, and 60% faced. So we see that the odds ratio now is very, very close to 1 in both cases. In fact, look at the p-values. The p-values are both insignificant. So I don't know the answer. I don't know why. Why do men tend to face the shower head to rinse their head, and women tend to give their back to the shower head to rinse their head? I don't know. I do know that I've been using this for a number of years now, and it always comes out this way. I must add, I didn't ask the second question about the length of hair, but that makes it so that it's unlikely that that is the reason. It certainly doesn't look like this is the reason. If you find a reason, please tell me about it, and I'll be watching the discussion pages to hear you out. Anyway, the bottom line of all this is that here we could investigate relationships between two dichotomous variables. Do you face the shower head? Yes, no. Are you male, female? Are you male? Yes, no. Or female? Yes, no. Do you have long hair, short hair? So 3 dichotomous variables. We could investigate all the relationships we would like to investigate with this. Now, the question is, can we extend this to the situation when we're not in this dichotomous, but rather we have 2 continuous variables? Okay, so let's generalize this. Not just that, let's also quantify this relationship. Just like we quantify the relationship with the odds ratio, let's quantify the relationship that we would like to find out about here. So here's an example of what I'm talking about. This appeared in the New England Journal just last month. And what it is, he did this tongue-in-cheek, I'm sure, but what it is on the bottom, on the bottom axis, where you've got the chocolate consumption, kilograms per year per capita. And on the vertical scale, you've got the number of Nobel laureates per 10 million population. And what you see is a sort of a linear kind of relationship between how much chocolate consumption there is in the country and how many Nobel laureates there are. This is your classical correlation analysis. Okay, and he found, I mean, he wouldn't be showing you this otherwise, but he found that this had a very, very high correlation, and he deduced that chocolate has some impact on your brain cells, and maybe that's why there is this correlation. I think he ignored the fact that the Nobel Prizes are Scandinavian, and you've got all the Scandinavian countries up here, but and not only that, Finland is down here because Finland. Enough said. All right. So there's an example. Now there is a problem with this. This, if we want to be serious about this, this study suffers from what we call the ecological fallacy. We'll come back to that before we leave this. Here's another one. And here, once again, we're dealing with countries. And here we've got the 5-year mortality rate per 1,000 live births. So that's an indicator of health level in the country. And what we've got here is the DPT immunization percentage. What percentage of the country is immunized? And here we probably see a closer relationship between immunization and mortality than you would in the previous graph. But nonetheless, this is at the country level, and what conclusions we can draw from this should be at the country level. Okay. At the personal level, remember we saw this amongst our own data. So here's the Framingham Heart Study, and this was the plot of at the first visit, and what we've got on the vertical is systolic blood pressure, and what we've got on the horizontal is diastolic blood pressure. And we see, remember we said, oh, look at this, there is this elliptical relationship that as the diastolic blood pressure goes up, the systolic blood pressure goes up, and vice versa. As the one goes down, the other one goes down. So they sort of vary together. They sort of co-vary, okay? They both vary, but they co-vary. They both go off in the same direction, hand in hand, all right? Now, can we quantify this? Well, what is this that we're looking at? Well, this is a little too amorphous. So allow me to do one thing. Let me center everything. Let me subtract the mean. So I'm heading towards standardization, but let me subtract the mean and therefore bring the origin here. So what this does is, from every systolic blood pressure, I'll subtract the average systolic blood pressure at visit 1. From every diastolic blood pressure, I'll subtract the average systolic, did I say systolic, diastolic? Well, for both anyway. Subtract the respective means. And then this is the plot we have. So when we do that, actually, let me put the back and fix the axes. So now I'm at 0 and 0. So there are the axes, and what do we see? Well, we're seeing the same thing we saw before, but there's too much. There's too much going on. So let me, instead of looking at all 4,400, whatever it is, let me just look at the first, 500, I'm sorry. Let me look at the first 500 subjects. So there they are. They're the first 500 subjects. How can we quantify what's going on? Ignore this part here in the center, because that's, things are sort of, they're small. The variability there is just very small and no big deal. But let's look at the bigger ones. What are we seeing? We're seeing the very, very big, very high above the mean, going in both directions. So this is very high above this mean, so that's the systolic. So the systolic is very high, and then also the diastolic is very high. In fact, these guys are up there. These guys, when they're very low, are also going together. Let me take out the center part. So what I've done here is I've erased, you shouldn't do this, of course, but just to show you what's going on, I've erased the diastolic, those with diastolic blood pressure between -5 and 5, and those with systolic blood pressure between -10 and 10, and here's what I've got left over. Now look at this. Look at the 4 quadrants. There's only 1 in this quadrant, and there's 2, 4, 6. 6 in this quadrant. Huge number in this quadrant, and a huge number in this quadrant. So this reinforces what we were just saying. How are we going to capture this with one number? That's our challenge. Well, let's go back to looking at these numbers on a chart rather than, on a table rather than on the graph. So here are the first 14 values. And here is this column gives me the diastolic blood pressure for patient 1, for patient 2, etc. And here I've got the systolic blood pressure with the same ordering. So the one who had the 70 diastolic also had the 106 systolic, okay? Now, what I've also done is I've replaced these by subtracting the mean diastolic blood pressure. So the mean diastolic blood pressure was 83. So I've subtracted 83 from 70, and I get -13. subtract 83 from 81, and I get minus 2, etc. And I did the same thing over here with the systolic, and I subtracted the mean systolic, which was 133. So 106 minus 133 gives me minus 26, and so on. So now ignore that. So now let's just look at the mean. So almost standardized. We can divide by the standard deviations, and then we get truly standardized variables. But that's not going to help us right now for what we want to look at here. So what are we seeing? Well, let's look at this one. Here's a big minus. A big minus goes with a big minus here. Here is another, that's a big plus. That goes with a big plus. Here's another big plus. That goes with a big plus. Here's a sort of a big minus. Here's another big minus, this time with a big minus. Big plus with big plus. Okay? Semi-big plus with a semi-big plus. They go together. So I've said this about 4 times in different ways right now, but they go together. Big plus with big plus, big minus with big minus. So what should we do? What happens if we multiply those together? Multiply the big minus with big minus, you'll get a plus sign. Big plus with big plus, you also get a plus sign, and a big number. So that's the kind of behavior we're seeing when they vary together. Okay? Now, when did we see this before? Think back to when we looked at the variance. What did we do with the variance? When we defined the variance, this was in the first week, we said, all right, we looked at the deviations from the mean, just like we've just done, and then we squared that, and we got the variance. In other words, we multiplied this guy, multiplied by itself to get this guy, okay? And that's exactly what we did with all of them. And that gave us the variance. So there was the variance. It was the average, and I just told you last week why we divided by n minus 1. And that was the average, and we took the sum of squares of the deviations around the variance. Okay, so that's when we had a single x. And we did this for the FEV1, and that's the variance we got there. We had 13 numbers, and that was the variance we got. All right, why not? Now we've got 2 variables. We've got an x and a y. Why not? Instead of looking at the variance, let me look at something called the covariance. Rather than multiply the x by itself, I'm going to multiply it with the appropriate y. So xi, so it's for the ith individual, and yi. And then average that out. That's called the covariance. This is the covariance. We could have called this the autovariance, but we don't. But anyway, so there's the covariance. This is how they vary together. They co-vary. All right? And now this was, and I said that this was almost standardized. We just centered them properly so that we had positive deviations going with positive deviations and stuff like that in that particular example. But if we want to standardize, then divide the y's by their standard deviation, divide the x's by their standard deviation. That's not going to hurt us at all. But what that does do actually is that, for those of you who are familiar with the Cauchy inequality, you will see that what that gives us is that this quantity, we call it R, it's the correlation coefficient, is always between -1 and 1. So doing that, standardizing, looking at the covariance between the standardized variables gives us this extra quantity, this extra quality, which is that now we standardize things. R is a pure number, and it always is between -1 and 1. Okay, with -1 meaning something very special, 1 meaning something very special, and we'll come to that in 1 second. But in the example that we looked at with the diastolic blood pressure and the systolic blood pressure at visit 1, we get that the correlation coefficient is 0.7842. Very high, close to 1, close to 1. but not quite 1. This is called Pearson's correlation coefficient. It's also called sometimes the product moment correlation. And here it is formally, if you've got n pairs of numbers, x1, y1, x2, y2, down to xn, yn, standardize the x's with their own mean and their own standard deviation, standardize the y's with their own mean, their own standard deviation, product, average out, and boom, voila. That is the correlation coefficient. Pearson did all the early work, all the mathematics on this, but this is really due to Francis Galton. Galton did a lot of the early work on correlations. He was pushing this. He was the cousin. He was Charles Darwin's cousin. And story is that he was a little bit jealous of envious of the cousin's famosity, if you will. But Galton also Galton was also left us with eugenics. I mean, he defined eugenics, the word even. Enough said. But Carl Pearson picked it up and put it into its mathematical framework, and that's what we use today. Now, very careful, very careful. This is a measure of linear relationship. This word linear, people sometimes ignore at their own peril. It's a measure of linear relationship. I'll try and explain what that means a little bit more. But here it is. The correlation coefficient is the average in the population of the average product of the standardized variables. So if you've got a population, you're measuring two things, x and y, then the correlation coefficient is standardize everything and multiply the two together, average out over all the individuals in the population. And we use the Greek letter rho to denote the population value of the correlation coefficient. Now, as I said, there are some very special extreme values. The one is at the one extreme, at the positive extreme, r equals 1. When r equals 1, then we've got perfect positive correlation. That's the biggest correlation you can have in the positive direction. And what it means actually is that there's a straight line. There it is. Y equals a plus bx. There's a particular a, there's a particular b, and there's your straight line. So you give me an x, I can give you a y. So they perfectly correlated. They basically a single variable that are related to each other by a perfect straight line. Okay, so once you know the one, you know the other. There's no two ways about it. So that's the perfect linear relationship. So note the relationship is linear. Okay. In general, though, a positive correlation just means that on average, the one goes up as the other goes up, or the one goes down as the other goes down. Okay, so they travel together. They're fellow travelers. They both go in the same direction, x and y. That's what positive correlation means. The other extreme, when r is equal to -1, means you've got perfect negative correlation. Okay, so the b is negative. So it's the same thing as before, except the relationship is negative, which means that as the one goes up, the other one goes down, and vice versa. As the one goes down, the other one goes up. But if you know the one, then you can solve for the other. In general, when you don't have this perfect correlation, then if you have a negative correlation, it means this on average, that the one goes up as the other one comes down, either the y or the x. Okay, so that's negative correlation. The other interesting point is right in the center when r is equal to 0. That means it's uncorrelated. Okay, so this is another word to confuse you. It's not independent. You might think it means the same thing. It doesn't. It means it's uncorrelated. It means you get this kind of picture that they're just all over the place, and there's no relationship between the x and the y. No linear relationship between the x and the y. Okay, be careful of that linear. What I'd like you to do, so this chunk is coming to an end soon. What I'd like you to do is go to this website, and there's a geeky nice game for you to play. And what you do is you go in there, and they throw up these 4 charts at you, and they also put up 4 correlation coefficients. And the game, and you can play with others, you can compete with each other, but the game is to identify each of these 4 correlations with a particular chart. Okay? So for example, this one, we see that these 3 are sort of tilted that way, and this one is tilted this way. So this one should be the positive correlation. And if we look, we see that 3 of the correlations are negative, and this one is the positive one. So I know the answer, so I was going to say, I would guess, well, I did guess, but that this one is the 0.78. So you fill that out as the 0.78. Now, the trick is to identify these 3, this one, and this one, with the other 3 numbers. Here's the tip. If they tightly, remember, if it's equal to 1, or in this case, -1, then they, boom, it's all lying on a straight line. But the further away it gets from 1, the more dispersed they get. So if we look at this, this one here, the bottom left-hand corner, is probably the tightest of those 3. So I would guess that that one is -0.82. And then I would say that this one here, bottom right-hand corner, is the next tightest. And so we're left with -0.34 as the top left-hand corner. You do that, you make your choices, and then you press answers, and boom, it gives you the answers. So in this case, I was right on all 4 of them. Go and have some fun and get a feel for this concept, this correlation idea, which is a measure of linear relationship that lies between -1 and 1. Okay? And I'll see you once you've done that.